could get started. What do you guys think?
Yeah, I'm always ready to get started.
Cool. So this is GNA, Global Network Architects. We're doing kind of like a session on VXLAN Design. We have a guest speaker here with us. His name is, where's my next slide? Oh, Said Nada. He has a CCDE and he has 2 CCIEs. And he's going to be explaining it. I do want to kind of see if anybody else has any experience with VXLAN. Ronaldo or Nor, do you guys have experience?
Yes.
Oh, cool.
A little experience, but I am CCIE in last year, and I have a little experience in VXLAN.
Very nice. Well, welcome. Glad that you came. So go ahead. I will let Said Nada take over, and if you have any questions, just feel free to ask. Are you going to share your screen? I'll go ahead and stop sharing. Go ahead. I think we can't hear you. Well, I can't hear you. Can you guys hear him?
No, it's really quiet.
Try talking again.
Can you guys hear me?
Oh yeah, that's great.
Yep.
All right. Thank you for attending, guys. And we're just gonna start with some hardware first, as like maybe basic knowledge for data center fabrics as opposed to VXLAN per se. So I'm gonna share my screen. Let me know if you see my screen here. Can you guys see my screen?
I see GNA. Yeah, I see it now. Data center fabric.
Okay, so we're gonna start first with the fixed form factor versus a chassis. And the reason for that would help you to determine which hardware should you be buying for your VXLAN fabrics or just spine leaf architecture. And it would tell you how many hosts would you have in your fabric and how much you can scale that fabric up to. And if you can scale up or you scale out. So first, the way the 1RU switches or 2RU switches mainly built, they are using one ASIC. And based on different types of ASIC, you can have like 100 gig boards or maybe like 6400 gig boards or 32 or some switches support right now up to 64 400 gig ports based on some ASICs, and we'll talk about this later. So when you decide to build a VXLAN fabric, you have to first scope the switches that you're going to be using as spine. And the spine switches would determine the speed of your fabric because that would dictate the connection between the spine and the leaf. So the way that the leaf switches, or the way that the switches are built, or 1RU switch or 2RU switch that is built with one ASIC, the forward traffic based on the switching engine in that ASIC. So technically, when a packet comes into the front panel interface of the switch, it would be intercepted by the PHY, the physical ASIC, and from there it will be brought into the TX ring. I'm sorry, it will be brought into the RX ring, and the RX ring would put that packet into a buffer. Then the header of that packet would be forwarded into the input queue, or some switches doesn't actually have input queue at all. So that header would be forwarded into the switching engine. However, the main or the data itself would be, or the packet is still in the buffer, and the switching engine would determine which interface that packet would be forwarded on. And after that the packet itself will be bridged in from the buffer into the output queue, or sometimes it will go to the TX ring directly, then the PHY, where the output interface is connected to. Now think about the same process if you're building the spine as a chassis. So the chassis would be actually having multiple line cards. Every line card is acting independently, and all of these line cards connected to what we call fabric modules in the back. And these fabric modules actually generate a spine leaf architecture within the chassis itself. So this is a change that will change the behavior of how you're building your fabric. So imagine now we're using a chassis. It's the same process again. The packet comes in, it will be delivered to the PHY, and the PHY would go into the buffer. The packet header would be forwarded to the switching engine, and the switching engine would decide where that packet should be forwarded. If the packet is forwarded on the same line card, great. It would be the same process that we have here. However, if the packet is forwarded on a different line card, that packet has to be delivered to the output queue or the TX ring directly, then the PHY, then that packet would actually cross the fabric line card or the fabric module within the chassis. And this is the first part of your fabric where you can have drops. They're still acting as switches, connecting the I/O line cards together, which is this line card and this line card here. And that packet has to cross the fabric line card to be forwarded to another PHY, which is different line card altogether. And from there, we repeat the exact same process until it leaves on the front panel interface. So this is the differences between the fixed form factor or one switch or a switch that runs with one ASIC versus a chassis that can actually have multiple line cards, and these multiple line cards connected to each other through the fabric. Any questions? So let's continue. So if you're using a chassis in your fabric as a spine, the way that these line cards are connected, they're actually presenting spine leaf architecture. So every one of these boxes here is actually representing a line card, and the way that these line cards are connected through the fabric line card. So thus, it is creating a spine leaf architecture, or you can also call it a claw fabric. That spine leaf architecture, if you have, obviously, when you have the leaves within your fabric, so the leaves will be connected to the front panel interfaces of your line card. So now you have moved your fabric from three-stage claw fabric into five-stage claw fabric. So if you're building a fabric that is hosting like some applications that are delay sensitive, make sure that you're choosing the right switch to run at a spine in order to achieve the minimal delay and in order to accommodate your application requirements. Again, this is the same diagram. So now if you take these leaves, they are connected into the chassis switch, which is your spine. You have converted your fabric from three-stage fabric into five-stage fabric. So there are some ASICs right now, like from multiple vendors that can support up to like maybe, as I mentioned earlier, 64 400 gig. This is the Tomahawk 4 from Broadcom, or can support 128 ports of 200 gig, or 256 ports of 100 gig. So imagine if you have a spine leaf architecture with two spines and multiple leaves. The leaves would be connected to both spines. The speed of your fabric right now that would be total of 200 gig. This is the speed of your fabric. And based on the number of the leaves that you have in your fabric, that would determine the total bandwidth of the fabric. So if you have 4 leaves within such a fabric, the bandwidth available within the fabric right now, that would be total of 800 gig. So also Broadcom has produced a new ASIC, which is Tomahawk 5, that supports 51.2 terabits a second, and that actually supports to 64 interfaces, 64 800 gig interface. The question right now, do we really need 800 gig interfaces on a switch? With the new buzz word AI and actually machine learning and artificial intelligence, you have something like a GPU that can actually process up to 900 gigs a second. Thus, you need a switch that can provide such such bandwidth per port. So if you have a server here, and with the new GPUs from NVIDIA that can like process up to 900 gigabits a second, thus you will need like one port that can deliver like the minimum of 900 gig, which is actually not necessarily happening in all companies now. However, with this new era of machine learning, we actually put a lot of pressure on the network to deliver such a bandwidth per second. So if you have a GPU that you need 900 gigabits per second, thus you will end up needing like at least, like if you have one GPU on that server, you will need like something to deliver up to 900 gig. I think the max that we have now is 800 gig per second. And if you have multiple servers within the rack, so actually take that same diagram and imagine this is a top of leaf switch and you have maybe 10 servers in this rack. Every server needs like total of 900 gig, and the max that you can do is 800. So on such switch, you will need to connect 10, maybe like 800 gig interfaces or more. And now the question would actually affect how are we going to build that fabric? How will I be able to provide enough bandwidth between the spines and leaf? How many spines do I need within the fabric? And now we're gonna get into actually, am I building a skinny fabric or this is actually called this skinny tree or fat tree fabric? And again, if you take that back to the GPU designs and like how much bandwidth I need to forward to these servers per second, you might end up actually building what we call skinny fabric, which is the input is equal to the output, which is like basically one-to-one subscription, which it can get very expensive if you do not have the right switches and like if you do not have the right ASICs in the switches that you're buying. And that actually can be a different vendor, whoever is actually using this ASIC within their switches. I'm not aware of a vendor using the Tomahawk 5 yet, but you can look up on the internet and see who's using the Tomahawk 5 into their switches to deliver 64 gig or 64 interfaces of 800 gigs. So the fat tree, usually there is oversubscription. So assuming you have a switch, maybe that have 64 100 gig interfaces facing the endpoints, and you're not necessarily going to connect total of, actually, if we say the 64 switch or a switch that have 64 ports of 100 gig, if you want to build a skinny tree, so 32 ports will be going toward the servers, 32 ports will be going toward the spine, and you end up building one-to-one skinny tree. However, most like fabrics that are being built nowadays, they're fat tree, where you have actually subscription of like maybe 3-to-1 or 4-to-1. And there is no rule if you go 3-to-1 or 4-to-1. It's based on your business requirements. Some people will say, oh, I want to be like Facebook or Microsoft, thus I want to do like 3-to-1. It doesn't necessarily make sense that it's going to meet your business requirement. Thus, build your fabric based on your business requirements, not based on a vendor telling you how to build your fabric. With Fat Tree, you can do 2-to-1. So if you have that same switch again, 64 ports with 800 gig interfaces, you can actually take a third of them, and this third would be toward the spine, and the 2/3 would be toward your endpoints. Thus, you end up like doing 2-to-1. Or if you divide it by 4, you take 3/4 of these interfaces and do it or have it toward endpoints, and that 1/4 to the spine, you end up doing the fabric as 3-to-1. Any questions?
No for me. No for me.
Great. So for the skinny tree, how do you calculate the number of endpoints that you can have within your fabric? So if you have like 3-stage claw fabric, it would be n power 2 divided by 2. So where n is actually the number of ports. So if you have a switch that have 64 ports, that would be 64 power 2 divided by 2. It will give you the number of endpoints that you can have within your fabric. And I believe I have an Excel sheet here. So let's take a quick example here. So actually, I'm going to go something 1-to-1. So if you have a switch, spine switch, that runs or have like 32 ports, every port of them is 100 gig, and you have 2 spines and total of 4 leaves. Every leaf is going to end up having 64 times like 100 gig. So basically from every leaf, you have 8 connections. So the 8 connections from the leaf with 4 leaves, you will end up using 32 ports on the spine. That would give you total of workload of 64 endpoints, and every point is connected to with 100 gigs. So technically, if you do the math of 32 power 2 divided by 2, it will give you the 64. You can just do it in the calculator real quick. And the same diagram here or the same Excel sheet can be used on the number of oversubscription that you're trying to create. So if you create an oversubscription of 2-to-1, so every leaf is going to end up having 3 connections. So 3 connections from every leaf. On a spine with 32 ports, you will end up using 30 ports on every spine, and there is 2 100 gig are not being used. And that leaf actually will give you total of 10 times the 48 ports front panel interfaces times like 25 gig, and that would give you subscription of 2-to-1. And this is here what we call fat tree. So if the input is equal to the output, that's called skinny tree. If you're doing any oversubscription, you're basically building a fat tree. So why would we use like fixed form factor over a chassis switch? So the fixed form factor, it can scale out. So I can add more spines, I can add more leaves in my fabric. So if you end up adding more spines, you're increasing the speed of the fabric. So if every leaf switch have 100 gig to the spines, so the speed of the fabric right now would be 400 gigs. If I want to get the total number or the total bandwidth that is available for me within this fabric, assuming that I have 4 spines and 4 leaves, I would have 1600 gigs available in my fabric that I can move traffic with. So the fixed form factor can scale out. It's agile. It would use actually like it would be less efficient from the electricity or the power perspective. However, you scale as you go. You don't end up building or like buying a chassis on day 0 with maybe 1 or 2 line cards and 2 soups, and you have 4 or 5 spots in that chassis available that you're not going to use. So basically, you end up paying for the chassis. However, if you scale as you go with fixed form factor as a spine, you only pay for what you need. So you can scale out within the fabric. However, you can scale up with a chassis as a spine. From the density perspective, you have higher density port perspective in a chassis. With the leaf, it is based on what ASIC, with fixed form factor, it is based on how many ports do I have connected to this ASIC and the switch model. Again, with the chassis, it is more efficient from the power. It's less, and the fixed form factor, it's less efficient from the power perspective. From the lock-in perspective, usually you have a higher lock-in, like vendor lock-in perspective on the chassis versus the 1RU switch, where you can actually specific vendors out there right now can go get an ASIC from Broadcom and just connect the ports to this ASIC and can, like, for example, the Tomahawk 5 that was 64 gig of 800 ports, or you can do like maybe 128 on 400 or yada yada. It doesn't really matter the number of ports in here. So it's sort of, there is a vendor lock-in, obviously, within the 1RU. However, some vendors go by specific ASICs on their switches, and voila, they can basically have the number of ports that they need. From the space and weight, obviously, it's a lot more complex to rack and stack a chassis versus 1RU switch. Sometimes you might even need a specific like lift if you wanna like rack and stack these chassis on top of each other or so. And obviously the 1RU switch, it's a lot more agile with the racking and stacking, and it's a lot faster to work with it. Cabling perspective, you will be using centralized cabling model versus like distributed cable model with the leaf. So it's easier to deal with a chassis when it comes to cabling. Position, it's like inflexible, it's harder to move. However, one RU switch, you can move at any time. And from the inventory perspective, it is very complex actually to have an inventory of chassis because they're expensive. You have 2 soups, you have fabric line cards. Do you need to keep those in your inventory all the time in case one of these line cards goes bad? Or do you have like 4 hours RMA from the vendor? You need to have a backup for yourself. However, you can keep like multiple RU switches because from the cost perspective, it will end up being cheaper as opposed to a chassis. Any questions or comment about hardware and why we're discussing hardware when it comes to data center fabrics?
No, it's pretty clear why you would need it and to know have that information.
All right, Ronaldo, what hardware do you use in your VXLAN fabric? Or you don't want to discuss it? Was that Ronaldo or
Sorry. Can you repeat, please?
what hardware do you use in your chassis or in
No,
your fabric as a fabric?
I don't use a VXLAN. I take my CCIE one year ago, okay, but is in enterprise, and now I change for start learning that data center, okay.
Okay. How about you, Magid? Magid Said. Do you use VXLAN in environment?
No, only in for training, EVE energy and other simulators.
Magid, do you use VXLAN? Like why you're interested in that, like training?
Yeah.
Magid? Oh, he doesn't want to come off mute. All right, let's move on. Any question thus far about the hardware and how do you choose a specific switch for your fabric? Okay. All right, now let's talk about the type of overlay. So we have what we call network overlay, and those will be terminated between the leaf switches within the fabric. And that can be MPLS, it can be Lisp, or VXLAN. So obviously with MPLS, you can run LDP or segment routing, and you can carry labels based on that. And with Lisp or VXLAN, they're pretty much still overlays, and these overlays are terminated between hardware. It can be a router or it can be a switch, it doesn't really matter. Also, we have what we call software overlay, where the tunnels would be established on the endpoint and terminated also on endpoint. Thus, the switches in between or the hardware in between do not get into encapsulating and decapsulation at all. And one example of that is what we call NSX, more specifically NSXT, that ran by VMware. We also have hybrid overlay where you can actually start a tunnel on a software as VMware, or to be more specific, NSXT, and that tunnel can be terminated on the hardware as a switch. Mainly, VXLAN is like vendor agnostic to an extent. So you can build a tunnel between a Cisco box and VMware or multiple vendors. However, when it comes to interoperability between vendors, things get more complicated because every vendor is still looking to do like vendor lock-in. They're basically do not want to open their boxes to communicate with other boxes in order to keep you spending money with them, obviously. With the software overlays, the encapsulation can be VXLAN, NVGRE, or Genève. The NSXT is actually now using Genève. There was an earlier version of NSX where they used VXLAN encapsulation. Anyone is actually using NSX on their network?
No, not right now. In the past, I had it connected to ACI in a different design that I didn't do, but no, not right now.
All right. Okay, so let's talk about VXLAN. So assuming you have already chose the switches within your fabric and you decided to use VXLAN. So you can use VXLAN to extend layer 2 or layer 3 between your leaves. And if obviously, like if you use VXLAN to extend it over layer 2, to extend layer 2, you're basically trying to get away from building large layer 2 broadcast domains, which is the data center have been struggling with for years. Like the larger you build your layer 2 domain, the more complex it gets. Thus, VXLAN can allow you to stretch a layer 2 domain over layer 3 within the underlay. And thus, the VXLAN tunnel will be built from one leaf to another. Mainly, the VXLAN tunnel is acting as point to multi-point, but with an overlay in general, you can emulate any type of network topology. You can actually end up building full mesh tunnels between all leaves within your fabric, as long as you extend all VLANs and all VRFs to the leaves within the fabric. It's not wise to do that though, because you end up like hitting some scalability limitations with specific switches where you extend all VLANs to all leaves as well as all VRFs to all leaves. Um, with with VXLAN, or if you're using VXLAN within your fabric to extend layer 2 and layer 3, the structure of the bucket itself is a little bit different than pure layer 3 network. So once you build a VXLAN tunnel between the leaves, all traffic crossing the spines would be actually encapsulated into what we call VXLAN header. So the spine is actually unaware of the original packet. So assuming that I have a VXLAN fabric, and I have two servers connected to this VXLAN fabric. If these two servers, server 1 and server 2, once talk to each other, assuming like they are within the same VLAN. So basically, server 1 would do like our request for the IP address, that have the MAC address and such. All of that part of the communication already has been completed. So when the switch gets that packet, it knows that the MAC address of server 2 is living on switch 2, and it would actually take that packet and it would encapsulate it into the VXLAN header. So that VXLAN header, or what we call the VXLAN ID, is equal to a VLAN. It doesn't necessarily need to be the exact same number, because now the VLAN number is actually more relevant to the switch. However, from the VXLAN perspective, it doesn't really matter. So I take that packet. So this is the original packet. I have my 802.1q in it, and I have my inner source MAC address, which is server 1, and the outer MAC the inner MAC address for the destination, and that would be switch 2. And the first thing that this switch is going to do, or you can call it VTAB. VTAB is basically a device that can start a tunnel and terminate it. And it will actually put the VXLAN header, which is the VNI. Then it will add an outer UDP header. The outer UDP header destination port will be 4789. So technically, I'm going to start a tunnel from, use a different color. I'm going to start a tunnel from leaf 1 to leaf 2. So that tunnel, the destination of it would be 4789, and the source port of that tunnel would be actually calculated based on the inner packet. So I'm going to take that packet, hash it, and based on that hash, that would be the source port of my VXLAN tunnel. And the reason for that is because you don't always, if it starts from a specific port and it is always terminated on a specific port, you will end up utilizing one link within your fabric, as opposed to all of the links between the leaves and the spine. So, however, if my source port of the tunnel is different, I will be doing hashing across multiple links. And the way that they randomize the source port is by taking that inside packet and like generating a hash, and based on that hash, I will use a specific or random source port, and that source port would be based on the 5 tuples. I would be selecting one interface, for example, between this leaf to send that VXLAN packet between leaf 1 and leaf 2. If I have different leaves or so, I will end up like doing sort of not necessarily load balancing, it's load sharing across all links between the leaf and the spine. And from there, I'm going to put my outer source IP address, which is the VTEP, and the outer destination IP address, which is the destination VTEP, like that I'm gonna deliver that packet to, and my outer 802.1q and the source MAC and the outer MAC. The source MAC will be that VTEP. Who's going to be my outer MAC? Anyone on the nose? Anyone on the call knows? What should be my outer MAC? My Vita? Does anyone on the call know? Will be based on my routing table. Where is that packet going to be delivered? That packet is going to be delivered to the spine. So from the layer 3 perspective, the layer 2 header is always rewritten per hub. So when that leaf looks into its own routing table, it will see that this leaf is reachable through the spine. Thus, my source MAC will be myself, and my outer MAC will be the spine, which is my next hub. When the spine gets that packet, it will actually remove the layer 2 header. This is just basic routing, and it would look into the outer layer 3, and based on that, it would rewrite the layer 2 header and send it. As everyone on the call now, the layer 3 header is actually rewritten in every hub. So
Yeah.
we have, all right, great. We actually have two different types of VXLAN. We have flood and learn, and we have EVPN control plane. The flood and learn doesn't scale very well. I think your max number of leaves is very limited. It's up to 16 leaves or so. This is actually based on a specific vendor documentation. However, the way to scale VXLAN is to bring control plane into it. And the control plane that they introduced within VXLAN was EVPN. With EVPN, you don't necessarily need to use the encapsulation of VXLAN header. You can use MPLS as well. As a matter of fact, EVPN has already been used in the service provider network for a while, where they actually forward based on labels. The difference, if any one of you coming from a service provider background or they have good enough understanding of MPLS, the way that MPLS forward packets, they need two labels to forward these packets, which is basically the MPLS label and the transport label. However, VXLAN can forward packets based on one label, which what we call the layer 2 VNI labels. If you have two hosts within the same VLAN talking to each other, I do not need anything other than a layer 2 VNI label to forward the traffic between the leaves. What forward the traffic between the servers is spread across multiple leaves. So to scale the VXLAN flood and learn, we actually, or they introduced a control plane. And obviously, when it comes to a control plane, BGP has been used as the kitchen sink of everything. If they need to scale something, or if they are out of ideas of how to solve a problem, they introduce a new address family with BGP. So we have EVPN address family with BGP, and that carries the information from one leaf to another, and it is reflected between the leaves across the spine. So if you're actually building a fabric with an underlay of an IGP and overlay uh, carrying the reachability as IBGP, you will have the spine running as route reflectors. So the spines would run as a route reflector within your fabric, and basically they carry the reachability across these leaves. Obviously based on some like conditions as well. So we have or EVPN is actually would carry the MAC plus IP as well as the network prefixes, and we'll talk about those in a bit. So I will also carry the VRF information. And if you're coming from a service provider network, or if you have a knowledge within service provider, there is something called route target and route distinguisher, where every route within the network will be like tagged with these two tags, route target and route distinguisher. So with the EVPN, we have two address families. Address family for the layer 2 VPN, which is basically extending the layer 2 across multiple leaves, or across PE if you're using EVPN within service provider. And we have a sub address family number 70, which is the EVPN address family. With to obviously to build something like that where you need to carry multiple VRFs and multiple VLANs, we're using the multi-protocol BGP. So in order to have multi-tenancy within my fabric, I'm going to be using VRF, which is like virtual routing and forwarding. You can think of it
Can I ask you a quick
as
question?
sure.
Sorry that I interrupted, but all right. So in the last slide, right? So what I was just out of curiosity, so which ones end up being your BGP peers, and which ones end up being your VTAPs, or should they be on the same device? So if the spines are your route reflectors, should they be the VTAPs and be the eBGP neighbors for the EVPN?
Not necessarily true. So the VTAB is equal to a device that is terminating a tunnel. So the spine can terminate a tunnel, or maybe in your design you have configured your network or your fabric for the spine not to terminate a tunnel. So the peering within this fabric would be a leaf. If you're using IBGP, would be between the leaves and the spine. So all leaves peering to the spine. However, the tunnel is being built from one leaf to another. The spine is
Yes.
nothing but a bridge. So if you can terminate a VTAB, or if you're terminating a VTAB on a device, that's where, or if you're terminating a tunnel on a device, that's what you call VTAB. So don't get too much confused, or don't get too confused between leaves and spines. Can you guys still see my screen?
Yeah, no, I can see you. I think someone joined that didn't mute themselves. Hey,
Oh, sorry about that.
no problem. Um, so yeah, I'm not too. I guess in a normal design, where do you
Mhm.
normally put like the VTAP, like on the
That
leaves themselves or the
on
spine?
on the leaves. So
Okay.
the spine, the spine is not necessarily going to be used as a VTAB unless you actually end up like using it as a border gateway or a border leaf to export the traffic to the core of the network. So always think of the VTAP as a leaf, where the tunnel ends and gets terminated. The spine is actually a transparent like device between all leaves. The only thing that it is doing is carrying or providing reachability between the VTAPs.
Got it.
Most designs you'll never see. It's a very limited like scenarios where you're actually gonna see the spine used as a VTAP. So most implementation, the VTAPs is between the leaves, and don't get too much confused between the the leaf names, because it's from marketing perspective, you're gonna hear data leaf, compute leaf, services leaf, border gateway leaf, border leaf. Um, all of that is just marketing. Um, border leaf, they say, oh, you use border leaf to connect to the outside of the fabric, or you can use it to connect to a firewall or load balancers. Other vendors will call that leaf a services leaf. Other vendors will call it just a leaf. So don't get too confused with the marketing term of like services leaf, border gateway. They do different functionalities from different vendors. So one vendor specifically, they have the border gateway where it can start a VXLAN multi-site to another fabric within your network where they can extend layer 2 and layer 3. However, a leaf is a leaf where the VTAB would start and a VTAB or the VTAB would be establish a tunnel to a different VTAB. It's based on the fabric that you're building. There, you can use most routing protocols within the fabric. Some vendors they say like it is best to use BGP in the underlay and the overlay. Some other vendors would say it is better to use IGP and the underlay and actually carry your overlay reachability in IBGP. So if you use IBGP, you will be doing route reflector because you're not going to have full mesh peering between all of your leaves. It doesn't make any sense. You just need that fabric to scale. Thus, we're going to give the spine like a job to do, which is a route reflector. Usually, every vendor would lean toward one protocol or not because their ASIC can do something or cannot do something. It's not necessarily a clean cut. We can do everything under the sun, and we're gonna give you a choice. However, the cleanest implementation I saw in when it comes to a VXLAN fabric is to use underlay as an IGP, and that can be OSPF or ISIS. Doesn't really matter what you use, and you carry your overlay reachability with BGP, more specifically IBGP, because once you start bringing IBGP in the once you start bringing EBGP in the overlay, now things gets more complex. So like you will be put in a space where should I use the same ASN on the spines and leaves? Should I have different ASNs between the spines on all spines? Should I have the same ASN on all leaves? It gets complicated, where you can actually end up having multi-AS design or dual AS design. With dual AS design, the spines will be in a specific ASN and the leaves will be in different ASN. But now you're gonna fall into like the BGP loop prevention mechanism where if I see my BGP ASN in a route, I'm not going to import it. So you have actually to go to every leaf and say allow ASN. And when you're using AS, multiple AS within the fabric, or even dual, now you fall into the complexity of the route targets. should the route targets be auto-generated, or should you use actually the same route targets manually on all leaves? So it's a lot more complex to use eBGP in the overlay. Just do yourself and everyone a favor and avoid it. And there is specific vendor is pushing for that, where you actually use BGP, eBGP in the overlay. And everyone have their own reasons, and they swear by it is best to use one versus another. However, it's mainly because one ASIC can do something and cannot do something, and the way they implemented they wrote the code in their network, or like their code, like their code does not do something specific. So do yourself a favor, just IGP in the underlay, uh, BGP to carry the overlay reachability. Any questions?
No, thank you.
All right, back to the MBGP. So the idea of the fabric is to be able, once you build VXLAN fabric, you want it to scale. So you can end up using multiple VRFs. And once you use VRFs, like you have to use route distinguisher, where you can actually, the route distinguisher makes something called, or the IP address plus the route distinguisher. This is what makes your route unique within the fabric. And we call that VPN route, or VPN v4 route to be more specific. The route targets, they're actually going to instruct the device on the leaf or whatever it is. It doesn't really matter. If you talk about it in a service provider network, where this route should be onboarded. Should it be onboarded in VRF-A or VRF-B? With EVPN, you're going to be mainly dealing with two routes. More specifically, EVPN type 2 and EVPN type 5. Those are the routes that you're going to be focusing on much when you have to do troubleshooting or after you build your network. So the EVPN type 2 route, that would be MAC or MAC plus IP. So what happens if this is your VXLAN fabric? Once a server is connected to that leaf, and that leaf, the port is turned up, the first thing that would the server do, it's probably going to try to talk to something, assuming you have an IP address. So it's going to do like an ARP to something, or somehow this leaf would learn that MAC address. That MAC address would be actually, it's based on the switch type. It will go into the MAC address table, and from the MAC address table, it will make it into BGP, and that would be type 2. For type 2, you will usually see two routes. One route only have the MAC, and the second route have a MAC plus IP. Obviously, if this device does not have an IP address, you're not going to see the MAC plus IP route within your BGP table.